In this video module, we are going to take a deeper look at BGP attributes and the best path selection process. We already talked about BGP best path selection process. In other words, we just glanced over it really. So now we are going to go in a little bit more detail. We are going to see how each of those attributes that have been considered in the BGP best path selection process can be manipulated and can be modified. What are the default values and what are the good sides or the bad sides of modifying those attributes, and what is the modification of the attributes or acting on those attributes. Those are BGP policies. But before we talk about BGP policies, let's remind ourselves about the BGP best path selection process. Now, we know that the BGP best path selection process begins only if the next hop attribute is reachable, if it's in a routing table. If it's not in a routing table, the BGP best path selection process does not happen for that particular network layer reachability information. Then weight, local preference, locally injected routes are going to be considered over remotely learned. AS path is considered the value of the origin code. Then the MED is considered. External routes are preferred over internal, lowest IGP cost, and then we have a bunch of tiebreakers. Now, when I went in the overview video, when I went over this process, I just left it at that, a bunch of tiebreakers. So what are those tiebreakers? Well, once you reach that point in the BGP best path selection process, the first thing that needs to happen is the BGP router needs to determine, is the BGP multipath used? BGP multipath is the configuration in which BGP is allowed to not choose one best route but use multiple routes to reach a particular destination. Unlike other protocols which automatically support multipath, which automatically support equal cost load sharing, BGP does not do that. BGP by default will always select the best route to reach a particular prefix. And if there are multiple paths to reach a particular prefix, by default, one of them will be chosen. But we can configure BGP for multipath. We can configure BGP for the internal multipath or the external multipath. But before we do that, we have to determine, is it going to be used? By default, BGP multipath is not used. So in that case, if BGP multipath is not used, then the two paths that are being compared are going to be going through this phase. If they are external, the older route is going to be considered. Now, if they are internal, then it will be the lowest neighbor's BGP route ID. So this part here below happens only if we have two internal routes being compared or internal and external. But we are not going to actually hit that situation with internal or external because that is being considered here. So beyond step 7, the only thing that can happen is that we have two internal routes or two external routes. So if we are dealing with two external routes, the older route will be preferred. But if we are comparing two internal routes, then the BGP router ID of the neighbors will be considered. There are situations when you are going to have the same BGP router ID. Now you might be thinking, how is that possible? Well, here's a simple scenario. Two routers peering directly from multiple interfaces. Now, routes learned over this session and routes over this session will both come with the router ID of this device. So it's perfectly legitimate, it's perfectly possible to have two routers with the same router ID. So if that happens, then the originator ID is going to be considered. If the originator ID is the same, then the cluster list will be considered. Now, these are the terms that have something to do with the process called BGP route reflection. So these are optional. These may not exist. If they don't exist, or if the cluster list is of the same length for the same originator ID, then simply the route that comes from the neighbor with the lowest IP address will be selected as the best. So these are the bunch of tiebreakers, as I like to call them, that happen if multipath is not used. Now, if multipath is enabled, what needs to happen is that weight, local preference, AS path length, origin code, metric or the multi-exit discriminator, and the AS path contents, that means that the actual autonomous system path that the route went through must be the same, then the route will be considered for the insertion into the routing table, but only if specific eBGP and iBGP specific additional rules are considered. Now, those rules are very, very esoteric, so what I recommend you do is you go to this link here and read about those details, even though if you reach this point in the BGP best selection process, you are already in trouble, in a sense that you have fairly non-deterministic behavior in your network. But in any case, what you want to do is you want to master at least these steps here, these steps you need to know and understand when you are learning about the BGP best path selection process. So let's now talk about BGP policies. When we talk about BGP policies, what we are actually talking about is the process of either acting on particular attributes or modifying BGP attributes to satisfy some requirements set forth in those policies. These requirements could be preferring a certain path over another path. It could be filtering certain routes that may have come from a particular autonomous system that match a certain access list or a certain prefix list. With BGP, you have a great degree of freedom how to define your policies. You can apply policies globally on the BGP process, in which case those policies that you have defined in such a way will apply for all the neighbors and all the routes. You can also apply those policies per neighbor, and per neighbor settings will obviously override global settings. And these per neighbor settings can be either set directly for certain things that support direct application of policies. Like, for example, if you wanted to use access list to perform some sort of filtering, you can use distribute list on the neighbor statement, either inbound or outbound, and in that distribute list you can perform filtering, or you can reference the same access list indirectly using the route map. In Cisco iOS and iOS XE, route maps are probably the most flexible way of filtering BGP routes. If you happen to be working with iOS XR, in iOS XR, things are a little bit different. There we have to deal with something called RPL, or the routing policy language. Now, we are obviously not going to talk about the iOS XR in this video series, maybe some other ones, but we are going to talk about the route maps. Now, good news about the route maps is if you understand how to use route maps to perform filtering for EIGRP or OSPF, you already know how to use route maps with BGP. The only thing is that you are not going to be acting on individual metrics, like for example EIGRP composite metric or OSPF cost, but you are going to be acting on attributes or sets of those attributes. Route maps can be applied on particular neighbor statements, or it can be applied at the injection point of those routes. Injection points are either moments when you redistribute the routes, or you want to insert routes using the network statements, or you're performing BGP summarization. All of these injection points support additional setting and modification of attributes using route maps. So route maps are probably the most flexible way of implementing our policies. We are going to go through a couple of examples later on, but I'm not going to go in detail about generic implementation of route maps, as we have already covered those topics. What I am going to talk about great deal about are individual BGP attributes and what they do and how can they be modified to implement certain policy requirements. In this section about BGP attributes, I am going to talk about BGP attributes in the same order they are going to be used in the BGP best path selection process. So let's start with our step 0. Our step 0 is the next hop attribute. Next hop is a well-known mandatory transitive attribute, which means that it will be present on every single BGP update. What next hop is depends really on where we are observing the route. It is usually going to be peer's IP address, and by that I mean when we have two external peers. So let's say that this is R1 and this is R2, and this one is in 65,001, and let's say that this one is 65,234. The example that we did have before, when the route is being advertised here, the next hop as observed on R2 will actually be whatever was the peer's IP address. So if this peering was implemented using directly connected interfaces like so, when this route is received on R2, it will have the value of this IP address here. In case of external sessions, this will always be true. When we have internal sessions, and we are yet to talk about a great deal about the internal sessions, the next hop by default will not change. So when this next hop here is advertised, it won't actually be the peer's IP address. It would be actually this IP address here. So it's very, very important to understand when the next hop changes, what it changes to, and how it propagates. And this is something that we will talk about a great deal when we talk about the external and the internal BGP peering sessions. For locally injected routes, it will be 0000, which really means there is no next hop, but because it's a mandatory attribute, it actually needs to be there, and it will be 0000 for those routes advertised by network statement or the aggregate commands. However, if we redistribute the routes, the next hop value of these routes, even on the router that is locally injecting these routes, will be actually the actual next hop of the redistributed routes. If it exists, if the next hop happens to be a local route, if the redistributed route happens to be directly connected route, in that case, we are also going to observe 0000. The important thing to know about the next hop attribute is that it must be reachable. Now, what this means is really it just needs to be available in the routing table. There is no further verification. Is it pingable? Does it respond to ARP inquiries? Do we have layer 2 resolution for it? In Cisco iOS, the only verification that is performed to make sure that next hop is actually reachable is that it is present in the routing table. If it's not in the routing table, the route will be invalid and will not be considered for the best path. However, if the next hop is in the routing table, even if it happens to be invalid for some reason, points to nowhere, for example, or to null zero interface, even in those circumstances, the next hop will be considered valid because it is available in the routing table. And I already mentioned that it remains unchanged inside the autonomous system. It can be modified, and in many cases it actually should be modified to different value, and between the autonomous systems it will be changed when the route is being advertised between them. Wait is Cisco proprietary, optional and non-transitive attribute. It is also a local attribute, which you will recall means that this attribute is local only to a particular router. What that means is when we have multiple routers that are using BGP, and it doesn't matter whether they are internal or external peers, whatever weight we have set for a particular prefix on this router will not actually be advertised to any of its peers. Same goes here and same goes here. It's simply a means to make sure that a certain route is more preferred than some other route for the same prefix on a local router. So it has a local significance. With weight, the higher value is preferred over lower values, and the default values are either 0 for all the routes that have been learned from remote peers, or 32,768 for all locally injected routes. And this means routes that have been inserted with the network statement, or that have been redistributed, or that have been inserted using the aggregation. Weight, obviously, just like any other attribute in BGP, can be changed. We can change it on per neighbor basis, and this is a direct change. And the syntax there is simply neighbor, and we would specify what is the neighbor's IP address, and we would say weight, and then we would specify the value of that weight. Now, what this command does is all the routes learned from this neighbor will automatically be assigned this weight. If you want to have a more granular control and you want to assign prefixes, say, you want to assign weights per prefix, for example, if they match some other attributes, you can always use route maps for that purpose. Now, keep in mind that you can set weight only using route maps only in the inbound direction, because if you try to set it in the outbound direction, the weight attribute doesn't exist in the BGP update, so it will have absolutely zero effect. Local preference is the strongest of the standardized attributes. What I mean the strongest standardized attribute, it is a well-known attribute. It is discretionary, which means it may not actually exist in all the routing updates, but well-known means it must be implemented by all implementations, all vendor implementations of BGP. What I meant by the strongest attributes is if we go through the best path selection process, we are going to see that the first attribute that we encounter in Cisco implementation of BGP is weight, which is Cisco proprietary. So weight is arguably the strongest attribute you can modify to implement path preference, but using local preference is the strongest standardized way, which is going to work across all the vendor implementations. When using local preference, it's important to remember that the higher value is preferred, which means that if you had two paths, one with local preference 100 and the other one with local preference 200, the path with the local preference set to 200 will be preferred. The default value of local preference is 100, but be on a lookout. When you are running certain show commands, like for example show IP BGP, you may not actually see the value for the local preference, but rest assured it's there. If you don't see it, it will be 100. The good thing about the local preference, and the name sort of implies that, is that the local preference will take effect across the entire autonomous system, which means that if we had multiple routers that form our autonomous system here, when we receive the route here, if we set the local preference to say 200 at this point, at the arriving point of this router, when this router advertises these routes or this route to these two neighbors, the local preference on these two neighbors will also be set to 200, because whatever we set on this router here will automatically propagate here. Of course, all of this behavior can be changed because you can use route maps to actually influence the local preference. You can use it inbound, you can change it outbound, you can modify it anywhere you like. Even when you inject the routes into the BGP using the network statement or the redistribution, or if you are performing summarization using the aggregate command, you can actually set the local preference to the non-default value. If you don't set the local preference to anything, it will be 100. Keep in mind though that if local preference was set to 200 inside this autonomous system, when this router here advertises this route outside the autonomous system, the local preference is gone, because it is, after all, a non-transitive attribute. If you want to influence the decisions made by another autonomous system, you would have to use different methods. It is, however, inside the autonomous system, possibly the most effective way to influence the path selection. What I mean by that is that it is a very strong attribute, it is standardized, it will take effect across the entire autonomous system. And if you are using confederations, which I haven't talked about yet, this decision, this influence will propagate to the sub-autonomous systems as well. It may not make sense what I'm saying with that right now, but when we talk about the confederations, it is going to start making a little bit more sense. So, local preference is a very good attribute to keep in mind if you want to prefer certain routes over another routes. Now, keep in mind, when you are modifying the influence of the incoming routes, the received routes, which the local preference is mostly used because it is very, very often used to set the preference when we actually receive the route from an external peer. In that case, what we are actually doing is we are saying, let's say that we are receiving the same route from two neighbors from two on two routers inside the autonomous system, the same one. So let's say that this is AS100 here. So if we set the local preference to 200 here and the local preference to 100 here, what we are really saying is that we would want to send our traffic towards that destination. Remember that it is always the incoming route means outgoing traffic. Outgoing route means incoming traffic. So setting the local preference to a higher value simply means that we are preferring to send the traffic towards that destination. If we want to influence the incoming traffic, or that means outgoing routes, we have to look at other attributes. One of the attributes that can be used to influence the decision made by another autonomous systems as to where to send the traffic, or in other words, which routes to prefer, is the AS path attribute. AS path is a well-known, mandatory, and transitive attribute, but in fact, this AS path attribute may consist of several components. What we usually call the AS path is actually a component of the AS path called the AS sequence. AS sequence is an ordered list of all the autonomous systems that this route has been seen in. Let me explain that in an example. So let's say that we had several autonomous systems that are somehow interconnected to each other. And let's say that this was AS1, or let's say that this is AS100, AS200, AS300, AS400, and let's say finally AS500 here. And let's observe some route N that begins its life in AS100. In AS100, this AS path is actually going to be an empty string. So I'm just going to represent it like this. So it's an empty string, or we can represent it with a set of empty quotes. Now, when this route gets advertised to AS200, the AS path becomes simply 100. Now, this 100 simply means that this prefix has been seen in AS100 before we received it here. Now, as this update travels throughout the autonomous system, the AS path inside the autonomous system 200 doesn't change. Now, it will change when this gets advertised to AS300. So here, the AS path is actually going to be 100, 200, but not in the order that you might expect. What we are actually going to see here is going to be the AS path that looks like this. So the AS path is actually built from right to left. So when we see the AS path that looks like this simply tells us that we have seen this AS in AS100 and then it was advertised to AS200. When this route gets advertised to AS400, what we are going to see here is going to be 100. Oh, let me move myself out a little bit. It's going to be 100, 200, and finally 300. Remember, it's built right to left. And then when this route gets advertised to AS500, what we are going to see here is going to be 100, then it was advertised to 200, then to 300, and finally to AS400. But this AS500 here, if we take a look at the route in AS500, what we are not going to be seeing is going to be our own AS here. Now, when we take a look at this path here, so let me just write it down here. So we have 400, then we have an empty space, then we have 300, then we have an empty space, 200, then we have an empty space, 100. From the perspective of the router on which we are observing this route, AS100 is something that is called the origin AS. Now, I would like to go out and say that this origin AS should not be mistaken with the origin code of the route. This simply means this is the autonomous system that first injected this route into the BGP domain. As this route gets advertised to our AS400, AS is 300 and 200, and sometimes depending on whom you ask, including 400 and actually 100, these all are going to be called transit autonomous systems. So this simply means that this route was advertised through these autonomous systems. It's not actually being terminated in these autonomous systems. 400, 300, and 200 are usually what's going to be called transit. Now, we are observing this in another AS that we are not going to see in the path, but we are going to treat AS 400, even though it is a transit AS, we are going to treat AS 400 as the peer AS. It simply means this is the autonomous system from which we, in our own autonomous system, actually learned the route. It's very important to remember these three terms, the peer AS, the transit AS, and origin AS, to understand what these terms actually mean. Now, going back here, let's take a look. So, AS sequence is an ordered list built from right to left. So it is built the other way than we would read, for example, English. Now, sometimes the AS path may have an unordered component called the AS set. Now, you might be thinking, what would be the purpose of the AS set? It is actually going to be used for the loop prevention in a case that we have BGP summarization that may summarize the prefixes that have different AS sequence. When that happens, the information about the original AS sequence will be lost, so AS path attribute cannot be used for the loop prevention. To avoid that, we can instruct BGP to actually insert all the autonomous systems seen in all the component routes of the aggregate that is being created in an unordered fashion, that they are simply there in the list, but we cannot determine where the route was learned, what are the transit autonomous systems, because this is an unordered list. When we have that situation, we are going to have another component of our AS path, which is going to be called AS set. This doesn't happen by default even when you create the aggregates. Actually, what is going to be set by default is an attribute that is called atomic_aggregate, which simply says that this route that we are observing has been aggregated by a particular autonomous system. And then there is going to be another attribute called the aggregator that is going to have more information about the autonomous system that actually performed an aggregation. But the actual components of the original AS sequences that made up this aggregate will be lost. If we create an aggregate in such a way, we might actually create a loop in our network. In order to avoid that, it's a good practice to use the AS set to prevent that loop from happening. And this can be done when you create an aggregate address. Now, you might be thinking, now he's going to say route map. It's actually not the route map. It will be a simple AS-set instruction, which is going to do two things. It's going to get rid of the atomic aggregate, and then it is going to create the AS set. When it comes to analyzing the AS sequence and using the AS path for the actual path manipulation, if we wanted to prefer certain path over another, in that case, we have to think about the AS sequence as a simple hop count. So we don't care at this point in our network that this path went through AS 400, 300, 200, and 100. What we care about is that there are actually 4 components of it. There are 4 autonomous systems in the AS path. So if we had 2 prefixes, one that had, for example, 400, 300, 200, and 100, and we had another that was, say, 200, 100, given that the weight and the local preference are the same, what's going to happen is this prefix here will be chosen because it has a lower hop count. So this is how the AS set the AS path is actually used to influence the routes. What can be done with the AS set is it can be modified using the route maps, but pretty much the only thing that you can do is you can add more autonomous systems to the path. And this is a common process, or the common procedure, the common method to increase the AS path length is to use so-called AS path prepending. Now, what is AS path prepending? Let's say that we are working in AS 100 and we have 2 peers here that both might be, say, receiving default or that are both receiving some network N. Now what we want to do is, for whatever reason, we actually want to receive traffic over this AS. So let's say that this is AS 200 and this is AS 300. So we want to receive the traffic for N over this link here. Now, if we advertised this in BGP normally, what's going to happen here, this will be the AS path here, and this will be the AS path here. What we can do on this session here, where we want to have lesser preference for our routes, what we can do is we can configure our BGP session to actually prepend our AS couple of times, 2 or 3 times. Now, take a look at this. This is the AS path that is going to be considered here. And this is the AS path that is going to be considered here. Given that AS 200 and 300 have the connections between them, AS 300, when it receives the update from AS 200, is going to have the AS path 100, 200, which is still shorter than this one here, which means that the traffic for our network N, it will actually go this way. And we have kind of accomplished what we wanted to do in the first place, and that is to receive the traffic for network N over this link and use this one here as backup. Now, keep in mind one thing, that is, while a perfectly legitimate traffic engineering method may not actually work, because in AS300, if AS300 set the local preference here to 200 for route N and left here the default for 100, the local preference will override our prepending settings. So if we want to influence the incoming traffic, what we can do is we can hint to the remote autonomous system, you know what, if you want to send us traffic for this network, we would prefer you do it elsewhere. But it is ultimately up to the autonomous system what it's going to do with its own traffic, because the local preference and the weight will both override the AS path length, which is the attribute that we are talking about here, or which is the AS path, but it's the AS path length that is considered from the traffic, from the best path selection process. In some very special cases, we can even shorten the AS path. Now, the command to do that is neighbor, and then the neighbor address, remove private AS. This is, as I said, a very special case. And it is going to be used in a situation that, let's say we had multiple autonomous systems here, and let's say that this was 65,001, this was 65,002, and this was 65,003, and let's say that this was AS 100 here. Or actually, you know what, let me use a slightly different example here. So what I'm going to do here is, let's say that AS 100 here is an ISP, and it has multiple customers. And these customers here are not big enough to have their own autonomous systems, so AS 100 actually gives them private autonomous systems to use and allows them to use BGP here. But when this AS 100 interconnects with, say, AS 200, which is another ISP, what we really don't want to advertise are these autonomous systems. Now, keep in mind that when this is advertised by default, the AS path, for example, for the routes coming from here would be 100, 65,001. Now, this 65,000 here is the private AS. So in this case, we actually want to get rid of this. We want to advertise just 100 because we want to hide the fact that some of these are using private ASs. This is the situation in which on this router here, for this peer on this side, let's say that this is peer X, we would say neighbor X, which and X is the IP address of this peer, and we would say remove private AS. So what that is going to do is, when the prefix is being advertised here, the router on this side is going to look at the AS path, and it's going to eliminate all the occurrences of the private autonomous system immediately preceding the AS that this router is actually in. So effectively, what we are going to do when we advertise the route for 65,001, to our ISP 200, what we are going to be advertising is simply going to be the fact that this is coming from AS 100, which in a sense is correct because these here are not real autonomous systems. They are private autonomous systems. If these hosts, if these networks here wanted to be multi-homed to multiple ISPs, in that case, this would warrant them going to ARIN or RIPE NCC or APNIC or whatever regional internet registry and actually obtaining their own autonomous system. Origin code is admittedly one of the most confusing attributes that students encounter when they are studying BGP. It's such a simple concept, yet it causes so much confusion. It is, first of all, a well-known mandatory transitive attributes. It has only 3 possible values, 0, 1, or 2. In iOS, this value 0, it is going to be shown as a lowercase I, and it actually has a mnemonic value of IGP. Value 1, it is going to be shown as EGP, and in iOS it will be shown as a lowercase e. It is very unlikely that you are never going to see this one. The incomplete origin or value 2 will be shown in iOS as a question mark. But what is this origin code? Well, let's take a look. So the origin code simply indicates to the rest of the BGP domain how a certain router injected the route into the BGP domain. So if we had, for example, here a connected route, let's call this network 1, N1. And if we have a connected route, that means that this route actually exists in the routing table. If we wanted to inject this route into BGP, we have several choices. The first choice that we can use is to use the network statement. Now, network statement, as you may recall, needs to be very specific. The actual network and the mask need to match exactly whatever route we have in the routing table. So this is a very, very explicit insertion of the route into the routing table. By default, in iOS, when we use the network statement to inject the route from the routing table into BGP, this will get the origin code of I. This indicates to the BGP that the routing table generated by non-BGP protocol, in other words, IGP protocol, and for that perspective, the connected route is treated as IGP by iOS. This indicates that this is how the route originated into BGP. However, if we had another route, let's say N2, and we wanted to inject this route, but not using the network statement, but we wanted to use that other option of redistribution. So if we redistribute, now granted, we could use a route map with the redistribute connected statement, but BGP treats this to be a little bit more crude, a little bit less specific than this one here. So these routes here that still need to be in the routing table, because remember, the redistribution is always done from the routing table. But because our injection method was less precise than the network statement, these will by default get an incomplete origin or question mark here. This doesn't mean that there is something unknown by them. It simply means that these are less specifically, less precisely inserted into the BGP domain. The third value for the origin, the lowercase e, indicates that this route was learned by a router using EGP protocol, which is no longer supported by iOS, and it hasn't been supported since, I think the last time I've seen it was back in 2000 or 2001, and it was version 11 or maybe even 10 of iOS. And don't hold me for that, because it's been a long time ago since this protocol has been gone from iOS. So you are never really going to see E, except maybe in some sort of learning lab environment where using origin of EGP is very often used in route maps to generate the routes that have different AS paths. But in real life, in production environments, you are very unlikely that you are ever going to encounter EGP. So the way origin code is used is simply lower value wins. That means 0 is preferred over 1 and preferred over 2. Now, this makes no sense mathematically, but this is how it is used logically. So we can say that IGP origin is the most preferred one over EGP origin over incomplete origin. But what confuses most of the students about origin code is if you do show IP-BGP, for example, to take a look at the route, you're going to have the information about the prefix, you're going to have information about the prefix length, you're going to see some of the attributes, you're going to see weight, local preference, and so on, and then you're going to see the AS path that is going to say something like, for example, 100, 200, 300, 500, and then I here. Now, most of the students assume that this I here means that this was an internal route. No, that doesn't mean that. This means that this route has origin code of IGP. However, sometimes in iOS, you are going to have a prefix itself that has a lowercase I prefix. Now, this I here indicates that this was an internal route. That's confusion number one. Confusion number two comes when there is no AS path, which means that this route is the local, it's local in this AS. It hasn't been learned from any outside AS. And answering the question, what is the AS path for this route? Students answer, oh, it's I. No, it isn't. It's simply an empty string, and in the display there, origin code is shown after the AS path. So this I here is not part of the AS path. So it is going to be shown after the AS path, but it may not be immediately obvious. The origin code is set at the injection point, and by default using network or aggregate will result in IGP origin code, as I explained, and redistribution will result in an incomplete origin. Of course, this can be changed. How can it be changed? It can be changed on either the neighbor statements or insertion point with route maps, and a simple statement in there that says set origin, and then whatever origin we want to set. If we want it IGP, we would set origin IGP. If we want it incomplete, we would say set origin incomplete. If we wanted set origin EGP, we can even do that. But keep in mind that that's a hidden command in most of the recent versions of the iOS. If there would be a contest about the BGP attribute with the most names, multi-exit discriminator or the multi-exit disk or MED or metric would probably win that contest. All these three names, multi-exit disk, MED and metric, refer to the same BGP attribute. This BGP attribute is a little bit misleading, especially if we consider the name that Cisco very often uses for it, which is the metric. We always associate, or we tend to associate, the word metric with something that makes ultimate decision which route is the best. Now keep in mind that in BGP we have a BGP best path selection process, and if you remember it, BGP MED is not very high in this list. It is actually going to be considered after all other attributes that we have talked so far about have been considered. And even then, it may not even end up being used. So allow me to explain all that. First of all, MED, or multi-exit disk, is an optional attribute, and it's also non-transitive. But you remember that I did use that little star when I first talked about the multi-exit disk. I'll explain that in a moment. If we end up using MED, the lower value will be preferred. However, in iOS, there is no default value for it, which means it's really missing, because it is, after all, an optional attribute. Now, in iOS, by default, a missing MED is actually treated to be 0 or the best value, because we are going to prefer the lower value. However, this can be modified in iOS to be changed that If there is no MED, if it's missing, it actually ends up being treated as the worst possible value. This can be done in the BGP process globally with the command BGP best path MED missing as worst. What BGP MED does, it actually influences a preferred exit point when peering with multiple peers in the same AS. Let me give you an example of that. Let's say that in this example we had two autonomous systems. Let's say here we had AS100 and here we had AS200. And let's say that we had multiple peerings between these two autonomous systems. So here I'm going to have two routers and here I'm going to have two routers. And let's say that there is a peering configuration that looks like this. Now in AS100 here, I have some network N that is somehow being advertised to these two routers. So I might have some internal peers here. And I want to advertise this network N to AS200. But what I would like to do is I would like to actually prefer the traffic over this link. Let's call this link number 1 and let's call this link number 2. And I really want to treat my link number 2 as the backup here. Obviously, one thing that I can do here is the AS path prepending, but another one is I can use the multi-exit discriminator. So on this peering session here on link 1, I could say, for example, I could set the multi-exit discriminator to 50, and on this one here, I could set my MED to 100. This multi-exit discriminator is then going to be received by this router here, and it's going to be received by this router here. Now, given that this MED 50 here is received on this router and that all other attributes up until this point have been equal, and that's actually crucial, that in order to make use of the multi-exit discriminator, weight, local preference, AS path length, and the peer AS must be the same. By peer AS, what I mean is that this attribute, all these attributes up until now, including the peer AS 100, must be the same in order for MED to be considered to be is part of the best path selection process. So on this router here, let's say that everything up until this point, up until MED, was taken into account. And this router here is also on the internal session actually receiving this route with MED 100. So MED 50 is going to win over MED 100, and this route here becomes best. And this is going to be the route that is going to be advertised inside autonomous system, and also to this router here, which is going to prefer the route with MED 50 over MED 100. So when we actually have some traffic to send to network N, even from this router here, we might actually end up sending this through our router here, because this is where MED has taken effect. However, where MED will be completely ineffective is in a situation that we had, let's say, 3 autonomous systems here, and let's say that we had AS100 here, and AS200 here, and let's say AS300 here, and let's say that we had peering sessions that looked like this. Now, let's say that these ASs 200 and 300 are both somehow, let's say that we had another AS, let's say AS400 here, that is advertising some network N. So this network N is arriving here, and this network N is arriving here. Now, mind you, at this point, this has the AS path, has the AS path of 400, and this one here will have also AS path as 400. So these two routers here advertise this route to our AS100, so the AS path here will be 200, 400, and here it will be 300, 400. We know that this is how the AS path looks. Now, if on this side here, in the inbound direction, I actually assign MED, so on this session here, I say, okay, I want to have this as MED 50, and on this side here, I want to have MED as 100, this will be ineffective, because if we take a look at what needs to be the same here, weight, let's say that the weight is the same, let's say that the local preference is the same, our 100 as the default AS path length, and if we take a look at the AS path length, in both cases it will be the same AS path length, so it will be AS path length 2, and then the peer AS must be the same. In this case here, our peer AS is not the same. On this side here, peer AS is 200 and here is 300, therefore MED must be skipped. However, this is not that uncommon situation that all these attributes are really the same up until this point, and the only thing that is really different is that the peer AS is not the same. In iOS, we can actually use MED in this situation as well, but we would have to configure the command BGP always compare MED. In that case, the only thing that is taken into account from the AS path will be the AS path length. That means that the peer AS restriction is no longer in place. MED can be modified using route maps, or when we are redistributing routes into BGP, we can use setMetric command. But there is one very important thing about MED, and this is about this star here. Now, we know that MED is optional non-transitive attribute, which means that it shouldn't really be able to leave our autonomous system. However, in this previous example that I used here, on this peering session here, in the outbound direction, I have actually configured setMetric equals 50. Now, setMetric is really the command in the route map that sets the MED. And here I did say setMetric 100. Actually, there is no equal sign there, so let me correct it in a case that you might want to use this as a reference. So there is no equal sign there in the syntax, so it's just setMetric 50. So if this was truly non-transitive attribute, this MED value would not have any effect in this autonomous system. However, it does. Where the non-transitive nature of MED comes into play is when we have more than two autonomous systems. Let's say that we had peering configuration that looked like this. And whatever actual configuration is inside this AS. And let's say that this is AS100, and that this here is AS200, and that this here is AS300. So inside our AS100, we have our network N, and let's say that we are advertising this network N with the MED equals 50 here, and the MED equals 100 here. Now, these routers here will select this as the best route, and this is the best route that is going to end up being advertised here. So does this mean that this router here will advertise this route with metric 50? Well, absolutely not, because this is where the non-transitive nature of MED comes into play. So from this AS, from the AS100, I can set the MED to influence decisions by my peer AS, but I know that this value will not by default actually leave that AS. However, what can be done here on this router itself could use setMetric to actually set the metric to a particular value. So it can set its own MED that is going to take effect in this iOS. Now keep in mind that there are two ways to set the metric. One is outbound, and the other one is inbound. When we set outbound, we are trying to influence the remote AS. What decisions are made in the remote AS? But when we set the metric inbound, we are going to be trying to influence our own autonomous systems decision. So it's very, very important to know whether you want to use inbound or outbound MED modification, and what are the actual consequences of using one or the other. What is going to be the end result of it. At this time, we have completed our overview of pretty much all the attributes that are directly used to influence the BGP best path selection process. However, there is one more important attribute called the communities attribute that I would like to talk about. This attribute is not directly used in the BGP best path selection process, but it can be used very effectively for route filtering and also route propagation control. The way to think about communities is as if they were really just route tags. Just like in IGPs, we have route tags that can help us filter the routes based on the contents of those tags, based on the value of the tag. The same thing is with the community. The only thing is that BGP communities are a little bit larger in value and they do have a standardized way that they are displayed. So the conventional way of displaying communities is the autonomous system :ID, where ID is really locally significant for that autonomous system. It's simply the tag value. So let's say that we had AS65000, and in that AS65000 we wanted to do something about the routes that had a special community that had this sub value of 100. So 65000:100 would be the value of that community. However, this is only how the community is displayed. The community is really just a very large 32-bit number. By default, in iOS, the communities will not be displayed in this format. They would actually be displayed as a really large number, and I can't even think of what this number would be. So if you want to see communities displayed in this format, you need to manually configure or explicitly configure a global iOS command. So this is outside the router BGP. This is the global iOS configuration command, IPBGP community new format. That is simply going to show you the communities in this format. The communities in BGP updates are always carried as really large 32-bit numbers. So as I said earlier, these communities, these route tags are not used for BGP best path selection process, but they're very effective for filtering. They are optional, but they are transitive, which means that if we set them in one AS, these will be carried into another AS. But again, in iOS, there is a little bit of a problem. The problem is that communities, by default, being optional, are actually stripped by default. So not only between the autonomous systems, but between the neighbors. So if we had routers that were peering directly, and let's say that this router here was setting some community, let's say 65,100, this router here would have this route, whatever the route was with this community, but by default when it advertises that route, let's say that it was 192.168.0.0/24, when this route gets advertised, at this point here, unless it has been explicitly configured to advertise the community, these communities, whatever communities were there, would actually be stripped from this update. If you want to use the communities and you want to advertise them to neighbors, what you need to do is configure the neighbors with neighbor, whatever the address of the neighbor is, send community. There are some sub options here, but I'm not going to talk about them now. They are a little bit advanced. So all you have to know at this moment that there are so-called standard communities and extended communities, and extended communities are communities that are mostly used for MPLS VPNs, and if you want to use those scenarios, in that case you might want to say neighbor send community extended or neighbor send community both. But if you just do neighbor send community, it's the same as saying neighbor send community standard, which are basically just the standard normal communities. Two things that I would like to mention about communities more. Unlike route tags, look at this. It says communities, which means that a single prefix can have pretty much any number of communities attached. So you can have prefixes that have multiple BGP route tags. That said, not all route tags are the same. Some well-known communities exist, and some of them, those three that I'm going to talk about now, have been defined in RFC 1997. And these three are no advertise, and by the way, this is the numeric value of it in hex. No export, and what RFC calls no export subconfederation, or as iOS calls it, local AS community. So what do these three do? Let me start with the simplest one to explain. No advertise. If the router has in its own BGP table, so let's say that we had here our three autonomous systems, like this. So let's say that this here was AS100, that this here was AS200, and that this here was AS300. And you know, let me expand this AS a little bit. So I'm just going to add maybe one more router in it. So let's say that this is R1, that this is R2, that this is R3, and this is R4. So let's say that R1 here is advertising to R2 some route. And when I say route, let's say that we are talking about 192.168.00/24. So what we want here is if this route here carried no advertised community. And by the way, in iOS, you don't have to remember this really large number for it. You can use the name for these well-known communities. So this number here I just gave you as a reference, as a kind of a joke, to be honest. You don't have to memorize these numbers in any way. You just have to understand that these communities, even though they are represented by names in iOS and in pretty much all the documentation, actually do have a large 32-bit number value associated with them. So let's say that there was this community no advertised attached on this route. So this route here did have this no advertised attached. What that is going to do is that it is going to cause that on R2 in the BGP table, this route exists with this community. Now, if the router has in its BGP table a route with a particular community that has associated behavior with it, and these three are well known, that means that they define a well-known behavior. If the router has in its BGP table a route, a prefix that has a well-known community, it must act, it has to act on what that community instructs it to do. So what is the instruction associated with no advertise? It simply tells this router, do not advertise this route to anyone. Not internal peers, not external peers, not anywhere. Now, to contrast this, let's say that this community here that was being set, so let me clean this up a little bit. So let's say that this community, that this route that was being advertised, this time had no advertise. Oh, sorry, no, we just talked about it. That it says that it has no export. So if it had no export community, what this would do, it would instruct this router not to advertise this prefix to any external peers, which means that R2 will advertise this to R3, but it will not actually advertise it to R4. The third example, the third community, in this scenario here, I'm going to call it by Cisco's name, local AS. In this particular scenario, it would work in the exact same fashion. So there is no difference in behavior in this scenario. However, there are things, or there is a concept in BGP for scaling internal peerings, and I am going to talk about it later on, that are called confederations, that are basically a large autonomous system number that has been divided into smaller autonomous systems. So let's say that this one here was actually 65,002 and this one here was AS 65,003. Now, they are going to be perceived by the rest of the world as AS 200. And let's say now that instead of using no export, R1 here advertised this prefix, whatever prefix was, with the local AS community, or as it is actually called in the RFC, it is called the no export subconfederation, which makes more sense than the local AS, I have to admit. So if it had this local AS or no export subconfederation, what this would cause on R2 is to not advertise this to other members of, or to other sub-autonomous systems. However, if R2 here had an internal peer in its subconfederation 65,002, and let's say that this was R5, this router here would actually receive the update. So, to recap, no advertise, do not advertise, to anyone, not internal peers, not other members of the confederation, not external peers, not anyone. No export simply means do not advertise outside your own AS. Now, in the case of confederations, that means do not advertise outside AS 200. With the local AS, that means you can advertise inside your own subconfederation, but do not advertise outside the subconfederation AS.